Good morning, everyone, and welcome back to Math 115. So today we're not going to talk about, or actually, wait, do we still need to finish 2.1? I think we do need to finish 2.1. So we're going to talk about 2.1 and 2.2 still. Your homework 1.8 is, or was due yesterday, and I assigned, oh, by the way, someone sent me an email. Alexa, I'll extend that for you, but let me email you about that after class. So homework 2.1 and 2.2 are going to be due on Friday. And when is your next quiz going to be? Your next quiz is going to be on this coming Tuesday. So a week from yesterday. And that quiz will be covering sections 1.6 to 2.2. So it covers the homeworks up to and including what is due on Friday. So that will be the quiz that's coming next week. So if you want to come to the office hours review for this quiz, that is going to take place in office hours tomorrow. Okay, so since that Tuesday quiz will come before Tuesday office hours, right? So the latest or the last office hours opportunity before this quiz will be tomorrow. So that is going to be when we review for the quiz. So that'll be probably not in my office because usually I feel like a lot of people come to the quiz review. So we'll do it in a classroom. I'll rent one out. Okay, and if you can't come to my office hours, of course, go to the tutoring center. Are there any administrative questions before we start in on content for today? Okay, then let's carry on. So let me remind you what we were talking about last time, which was, wow, we covered a lot last time, huh? Okay, what we talked about last time was more quadratic functions. Okay, so we recovered this example where we transform or convert from standard form into vertex form. So why was vertex form important? Vertex form is important because it makes it easy to graph the quadratic using the graph of x squared and then just apply your transformations. Okay, then we talked about the range of quadratic functions. We talked about the discriminant. Of course, the discriminant told us basically whether our I need to find a place to draw. Whether our parabola was basically one of three types. The first type is that it touches the x-axis twice. The second type was that it touches the x-axis just once at the vertex. And then the third type was it doesn't touch the x-axis at all. Okay? So that was what the discriminant told us. And it had to do with what was under the square root. If what is under the square root is positive, we get two real roots. If it's 0, then we just get one real root. And if it is negative, then we get no real roots. We actually get two complex roots. Okay, so that was the discriminant, which can be used to tell how many x-intercepts does a parabola have. Okay, so then we started talking about a wider class of functions called polynomials. So quadratic functions are also polynomial functions, but not necessarily the other way around. So the degree of the polynomial is just the largest power of x that we have. Of course, all of the powers of x for a polynomial are going to be whole numbers, whole positive numbers, right? So if the largest degree was 2, we call it a second degree polynomial or a quadratic. If it was 3, we call it a cubic. If it's 4, we call it a quartic. If it's 5, we call it a quintic. And I gave you the amazing story of the French terrorist who came up with the idea that the 5th degree polynomial is not solvable by radicals. Okay, so then we discussed the graph of polynomials, which are smooth and continuous. Okay, so a graph of a polynomial will never have a kink, and it will never have a jump. The domain of polynomials is always all real numbers. Then we talked about power functions. Power functions are not necessarily a polynomial. They are functions of the form a times x to the n, where n is just a real number. Okay, n is a real number, which is not 0. So you could have something like 3x to the 1/3, right? That's a power function, but not a polynomial. But some power functions are polynomials, namely if the power n is a positive integer. Okay, so those were power functions. Even an odd degree was self-explanatory. And then we talked about end behavior. Okay, so we introduced this new notation about limits, okay? So we talk about the limit as x goes to infinity of a function. We want to think about what is happening to the value of the function when the input becomes arbitrarily large, or when the input becomes arbitrarily large and negative. So this is called the limit. And we saw some examples. Okay, the limit as x goes to infinity of x squared. Okay, it just goes up and up and up forever. So we're talking about what is happening to the height of the function as the x values become as large as we want. Well, the height of the function also becomes as large as we want, albeit somewhat faster, right? Because it's x squared. Okay, so then we talked about a different one where we had there's some situations where, well, if the power is odd, we might be going to negative infinity, right? Or something like that. So end behavior, we learned for a polynomial is completely determined just by the largest power of x that we have. So we did an example where we showed, okay, if I have a sum of x to the 5th minus x to the 7th plus x squared, the only term that matters whatsoever for determining the end behavior is the largest power of x. So that way we said, okay, when x goes to positive infinity, I'm not going to worry about this term. I'm not going to worry about this term. I'm just going to ask myself, what happens to the value of negative x to the 7 when x becomes arbitrarily large? And the answer is, it becomes arbitrarily large and negative because of this minus sign. Okay, so that was end behavior. Then we talked about the zeros of a polynomial. So we had this sequence of equivalent statements. Okay, c is a 0 of f, x equals c is a solution of the f of x equals 0 equation, c is an x-intercept of f of x, c comma 0 is on the graph, and x minus c is a factor. Okay, so big star for number 5. Okay, if c is a 0, then x minus c is a factor of the polynomial. That's going to be important later on. So we practiced finding the zeros. This was basically just review. We take out a GCF, right? Take out a GCF, then factor, and we get the zeros of f of x. And I think that's not where we stopped. The last thing we said was, what is the intermediate value theorem? And the intermediate value theorem has an unbelievably simple, intuitive explanation. Which is that basically if I am participating in some kind of continuous process, if I start at one point and I end at another point, then I must have at some point in between been at every intermediate point. That's why we call it the intermediate value theorem, right? So what does that mean? That means imagine that this is time A and time B, right? If at time A I'm flying an airplane at this height, and then at time B, sometime later on, I am flying an airplane at this height, then for every height which is between these two heights, right? For every c which is in between the height at the start and the height at the end, then I must have a corresponding time in between my starting time and my ending time, such that I was flying an airplane at that height, or at this height, or at this height, or at this height, right? This has to do with the fact that the function is continuous, right? I have to draw it without picking up my pencil, right? So no matter what height I choose in between my starting height and my ending height, there is a point somewhere in the middle that achieves that height, okay? So let's take one closer look really quickly at the mathematical statement of that. We say A is less than B, okay? These are our inputs. If f is a continuous function, and this is an extremely crucial condition, f must be continuous, then for each value c, which is in between the outputs, okay? In between the outputs. So we have the inputs and then we have the outputs. For each value c, which is in between the outputs, there is an input, which is in between the starting input and the ending input, such that the height of the function at that input is equal to the value c, which we choose between our starting and ending output. Is that very confusing? Or how do you all feel about that? Let's do some thumbs. How do we feel about the... Oh, maybe I should make this full screen. Let's have some thumbs. How do we feel about the intermediate value theorem, the mathematical statement of it? Thumbs up if we feel great, hold them high. Thumbs up if we feel great, thumbs down if not so much. And somewhere in between if we're in between. Okay, that's pretty good. At least it's about what I was hoping for, because this is one of the more abstract pieces of reasoning that we will encounter. So let's see an example of the intermediate value theorem in use. So this is verging on proof-based mathematics. So what is proof-based mathematics? Well, the difference is, something like find the zeros of this function. It's a rote calculation, right? I do a process, okay? So I'm just rearranging. It's not really a proof, it's more of a calculation, right? So if I want to answer a question like this one, which says, use the intermediate value theorem to show that this function has a zero between x equals 1 and x equals 2, then I'm not talking about a calculation so much as I am talking about a formula argument, right? So I want to say that something is true. And any time in mathematics or in the court of law or in a philosophy paper that you want to say that something is true, you need to provide evidence, right? You need to provide evidence that that thing is true, right? So that's what we're going to do. So I have this intermediate value theorem, right, which tells me as long as certain conditions are met, I get a result. And I'm going to apply this theorem in the context of this problem to prove that the function f of x equals negative 2x cubed plus 4x plus 5 has a zero between x equals 1 and x equals 2. So let's see how that's going to happen. Okay, so the very first thing that I'm going to say is, well, if I'm going to use the intermediate value theorem, then there is one condition that must be met before I can apply it. And that is a condition on the function f of x. Can anyone tell me what that condition is that I must have for f of x in order to use the intermediate value theorem? That's exactly right, Andrew. F must be a continuous function. So I must give a formal argument for why f of x is continuous. F of x is continuous because what? Because what? Why? Why should this function be continuous?
Because it's a polynomial.
Very good, Sully. It is a polynomial. And we learned that the graphs of polynomials are always smooth and continuous, right? So f of x is continuous because it is a polynomial. So, therefore, I can use the intermediate value theorem. So, what do I need to do to use the intermediate value theorem? I have my input and my output, I have my two inputs, but I need to find my two outputs, right? So let's find them. Here's x equals 1 and here's x equals 2, right? So what are the outputs going to be for x equals 1 and x equals 2? How am I going to find them? Well, I'm just going to do f of 1, which would be negative 2 times 1 cubed plus 4 times 1 plus 5, right? So if I'm not mistaken, this would be negative 2 plus 4 plus 5, which is 9 minus 2 is 7, yeah? So the height of the function when the input is 1 is 7. All right. Now let's find what is the height of the function when the x value is 2. Well, we would get negative 2 times 2 cubed plus 4 times 2 plus 5, which would be negative 16 plus 8 plus 5, which is negative 8 plus 5 is negative 3. Yeah? Okay, so the height of the function when the x value is 2 is negative 3. So we put a point right here. That is on the graph of this function. So can someone help me finish this off? Why should it be true that the function f of x has a 0 between x equals 1 and x equals 2 based on this picture? Why should that be true?
Because the function is continuous, those lines will connect, and therefore it has to go through x is equal, or y is equal to 0.
Yeah, exactly. Griffin's got the right idea. What I need to do is, f of x is a continuous function, right? So what I need to do is, if I was going to draw the graph of this function, I would need to connect these 2 points by a smooth curve. If I connect these 2 points by a smooth curve, it must pass through the x-axis. You see how that is true? If I'm going to connect this point and this point, there's no way that I can go around the x-axis. I have to go through it. Okay, whether it looks like this, or it could look like this, or it could look like this. You know, it could look like anything. But it has to go through the x-axis at some point if we're going to connect these 2 points by a smooth curve. Okay, so since f of 1 is larger than 0 and f of 2 is less than 0, there exists, why don't I not use that notation? There exists an input x naught, which is between 1 and 2, such that f of x naught is equal to 0. By the intermediate value theorem. Okay, so this is a totally different type of problem than probably you're used to doing. You're used to things like find the zeros, where it's very much just compute, 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 right? But this is something different, right? This has a totally different flavor. It's a formal argument, right? I say, well, I know the function starts above 0 and it ends below 0. And since the function is continuous, I know that there is a theorem which says that the function will take every intermediate value between that height at the start and that height at the end. And since 0 is a value which is between my starting value and my ending value, I know that there must be an x value somewhere in the middle such that the function value is equal to 0. And I say absolutely nothing about where that x value is. I just say it has to be somewhere in there. Yeah? Okay, so this is more of like a logical conclusion than it is a computation. Are there any questions on this problem? Because this is definitely, is most likely different than anything you've done in math recently. Okay. By the way, this is what math will, if you take math to a higher level, like into the upper division classes at U of SC, This is what math, for the most part, becomes. It's these types of formal reasoning and proof-based mathematics. So once you learn how to do like pretty much most of the computations that you will need, it becomes much more about making formal arguments like this. Okay, well, that's all I want to say about that. I guess we'll move on. So let's talk about the number of zeros that a polynomial will have. Okay, and okay, so what is the number of zeros? Well, if you have a polynomial of degree n, then it has at most n real zeros. Okay, so let's see an example of that. An example would be something like x plus 1, right? That is a polynomial of degree 1, right? And it has how many zeros? 1 zero. Namely, what's the zero of this polynomial? X equals -1, right? That's what would make that 0. Okay? Okay, or we could do something like this. X squared minus 1. Well, we could factor that, right? That would be x minus 1 times x plus 1. And so it has how many zeros? It has 2 zeros. Namely, x equals 1 and x equals -1, right? So the number of zeros of a polynomial is going to be, at most, its degree. The number of real zeros will be at most n. Okay, it could be less than n. Let's see an example of when it could be less than n. Well, let's take a look at this function, f of x, and I put it into factored form, right? How many zeros does this function have? Definitely x equals 1, right, is a 0 for sure, because that would make, not 1, x equals -1 would be a 0, right? Because that would make this thing 0. Are there any other zeros? Is there any number I can plug in here that it would make this factor equal to 0? No, there's not, right? Because if you take a number and you square it, you get something positive, right? And if you take something positive and you add 1, it's definitely not 0. Yeah? So there's no way to make this expression 0 without introducing complex numbers. So it has 1 0. Someone help me. What is the degree of this polynomial? So I might be tempted to say, well, the degree is the largest power of x, right? So the largest power of x I see is 2. So is this a degree 2 polynomial? No, it's not. Can someone give me reasoning why not? Yeah, Lauren?
Because if you factor it, if you FOIL it, then you get x cubed.
Exactly. If we FOILed this, what would we get? We would get x cubed plus x squared plus x plus 1, right? That would be what we get if we FOIL this, if I'm not mistaken. So this is a polynomial of degree 3. So when we're talking about the degree of a polynomial, we need to think about it in terms of, well, if I totally FOILed it out, what would be the biggest power of x that I have, right? Okay, so this is a degree 3 polynomial. And it has exactly 1 real zero. Okay, so that's the kind of baby version of a massive theorem in mathematics called the fundamental theorem of algebra, which says basically if you have a degree n polynomial, if you count complex numbers, a degree n polynomial has exactly n zeros, counting multiplicity. Okay, that's the fundamental theorem of algebra. There's something like 1,000 different proofs for it. And people, math professors, have competitions of who can come up with the silliest proof of the fundamental theorem of algebra. All right, so that's about the number of zeros that a polynomial has. Now let's talk about what does this word multiplicity mean that I just said. Okay, well, if x minus c to the power m is a factor of f of x. So in particular, x equals c is a 0, right? X equals c is a 0. Because if I plugged in c for x, I would get 0 here, and 0 to the m is still 0. But if x minus c to the power m is a factor of f of x, then the 0 x equals c is said to have multiplicity m. Okay, so for example, here we have a function, we have 3 zeros. X equals 0 has multiplicity 2, and x equals negative 1 has multiplicity 1, and x equals 2 has multiplicity 1, right? So why is it multiplicity 1? Because I could think of there being like a power 1 here, right, on each of these factors. Okay, we just don't write it because anything to the power 1 is just itself. Okay, so that's about the multiplicity of a 0. It has to do with how many times that factor shows up in the factored form of that polynomial. Any questions on multiplicity of zeros or how many zeros we expect a polynomial to have? Okay. Doesn't seem like there are any questions, so we'll move on. Let's talk about turning points. Okay, so this is not really this is not really algebraic or analytical, but it's really just a graphical statement, okay, which says something about the graph of a polynomial. So what does it say? It says if our polynomial has degree n, then it has at most n minus 1 turning points. Okay, it has at most n minus 1 turning points. So let me show you what I mean by that. So this one is what? X to the 4 minus 7x squared minus 18. Let's check what that looks like in Desmos. It was x to the 4th and then minus 7x, fuck, I always forget. Minus 7x squared minus 18. So minus 7x squared, and then minus 18, right? Okay, let's see how many turning points we have. What do I mean by a turning point? What I mean by a turning point is this, or this, or this, right? Where the graph turns around, okay? So, if we have a polynomial of degree 4, like we have here, we should expect at most 3 turning points, okay? Could be less. It could be less than 3 turning points. But this is a degree 4 polynomial that does have 3 turning points. 1, 2, 3, right? It's where the graph turns around. And by turns around, if you want to make that statement a little bit more mathematical, it means the function goes from being decreasing to being increasing, or vice versa, right? This is an example of one where it goes from being increasing to being decreasing. The point at which that occurs is what we call a turning point. Okay, so that's what I mean by turning point. So what do we say? We say if the polynomial has degree n, it has at most n minus 1 turning points. But it could have fewer than that. Let's see an example of when it has fewer. Here's a degree 3 polynomial, x cubed. We should know what x cubed looks like, but let's see it anyways. X cubed looks something like this, right? So remember, a turning point is where we go from being increasing to decreasing, or where we go from being decreasing to increasing. How many turning points do we have in this picture?
1.
Do we think 1? Do we agree with that? Well, let's take a look. This would be the likely candidate, right? But is this a turning point? No, why is this not a turning point?
Still going up.
Because we go from being increasing to being increasing, right? for it to be a turning point, we would need to start going down. Okay, for it to be a turning point, we would need to start going down. So this is a polynomial of degree 3, which has 0 turning points. Okay? So the number of turning points could be less than the degree. Okay, so that's 2 examples. Any questions on turning points? Okay, if you take calculus, you'll learn more about these turning points, which could also be viewed, by the way, as local maximums or local minimums, right? So if you learn calculus, you'll learn all about how to find where they are. Okay. Let's move on and talk about how do we sketch polynomials. Okay, so we've talked about all of these different features of the graphs of polynomials, and we've talked about, okay, where are their endpoints? Okay, where are their zeros? Not endpoints. What is their end behavior? Where are their zeros? What else have we said? Okay, how many turning points are we going to have? And anything else? I guess that's all we've really talked about so far. We're going to learn another thing here, which is going to help us round out our understanding of the graphs of polynomials and help us to be able to sketch them, okay, without using a graphing calculator. Okay, so let's see what happens at a 0 of a polynomial depending on the multiplicity. Okay, so if the polynomial has a 0, like x minus c, and the multiplicity is just 1, so the factor is just x minus c, right? Then what is going to happen at the point c, at the value c, the function is going to go through. It is going to pass through the x-axis, okay? And depending on whether it's going down or going up, it will look like one of these two, right? It will go right on through. Okay, what if the multiplicity is even? Well, if we have something like x minus c squared, or x minus c to the 4th, or to the 6th, right? Then what's going to happen is the function is going to approach that 0, it's going to touch 0 at that point, and then it's going to stay on whatever side of the x-axis that it was already on. Okay, so I call this the difference between passing behavior, that's when we go through, and bouncing behavior, that's when we touch and then bounce off of the x-axis. Okay, and one final comment is if the multiplicity is odd but larger than 1, okay, so something like x minus c cubed is a factor, then we are going to still pass, but when we pass, we're going to sort of flatten out, right? This looks kind of like the graph of x cubed, right? Where we flatten out as we get close. So we will flatten out, but we're still going to go through, all right? So if we were going the other way, it would look like this. We'd flatten out, but we'd still go through. So odd multiplicity tracks with passing behavior. Even multiplicity tracks with bouncing behavior. Okay, so let's see one more thing here. Actually, okay. Yeah. So what do I want to say? The other thing I want to say is that other than the zeros, okay, which is where the function touches the x-axis, the other one useful thing that is useful to graph a polynomial is going to be the y-intercept, right, where it touches the y-axis, right? How do we get the y-intercept again? I plug 0 in for what? For x, right? To get the y-intercept, I plug 0 in for x. If I want to find the x-intercept, namely the zeros of the polynomial, then I set the polynomial equal to 0. Okay, so 2 different situations there. So let's put it all together now and try to graph this function. So the nice thing is that they have already factored this function for us. They've already factored. Okay, so all I'm going to do is determine the following things. I'm going to look at the end behavior. I'm going to check zeros and multiplicity. I'm going to find the Y-intercept. And then I'm going to graph. I'm going to sketch. Okay, and this is sort of imprecise. But let's think about this. If I were to FOIL this out, what would be the largest power of x? Well, I have 1 power of x here. There's 2 powers of x here. And there's 1 additional power of x here. So how many do I have in total? 4. So this is a degree 4 polynomial. And what would the leading term be if I were to FOIL all this out? The leading term is the largest power of x and its coefficient. What should it be? Yeah, negative x to the 4th power, right? Why negative? Because I have a negative sign here. So I'd FOIL this, with this, right? And I would get x to the 4th, and then I would make it negative because there's a minus sign there. Okay? So the leading term is negative x to the 4th. So let's determine end behavior. Well, I know that end behavior only depends on what? What does end behavior only depend on? The leading term. Good. End behavior only depends on the leading term, which in this case is negative x to the 4th. So what is the limit as x goes to infinity going to be of f of x? Well, as x becomes really, really big, what is going to happen to x to the 4th? Well, negative x to the 4th is going to decrease, right? But just x to the 4th is also going to get really huge, right? Think about plugging in something like 1 billion. Well, if I take 1 billion and I take it to the 4th power, it's gotten even bigger. Okay, it's even bigger except it's negative. So what is the limit as x goes to infinity of f of x? It's going to be negative infinity, right? Okay, and how about the limit as x goes to infinity of f of x, not infinity, but negative infinity? If I do negative infinity, then the limit should just be whatever the opposite is, right? Should it just be the opposite of what we had before? No. What? Why not?
Because it's even, so no matter what, once you power it, it'll be positive and negative.
Exactly. Griffin's hit the nail on the head. Because it's an even power. I know the end behavior is the same on both sides, okay? It's the same on both sides. It should be minus infinity, okay? And here's why. If you plug in a negative number and you take it to the 4th power, you get the same thing as you would if you plugged in that number but positive, okay? For example, negative 2 squared is the same as 2 squared, right? Or to the 4th, or whatever you want to do, right? So I just get the same exact thing for x to the 4th, and then I have to make it negative, right? It'd be a whole different deal if there were parentheses here, by the way. If there were parentheses there, that'd be a whole different deal, but there's not. Okay, so this is our limit. So let's see, what am I going to do in terms of the graph for this? Well, in terms of the graph, what I know is that when x is really, really big or really, really small, or negative, really, really negative, then the function value is becoming very, very negative. So I can start to fill in what's happening on the left side and the right side. I know generally at the end it's going to go down, right? It's going to go down on each side. Okay, and then I'm going to fill in whatever happens in the middle, yeah? Okay, so let's see how that works. So the next thing to do is to check the zeros and the multiplicity. Okay, that will determine the passing or bouncing behavior. So I have 3 zeros, right? I have x equals to -4 has multiplicity what? Multiplicity 1, which means I'm going to have what? Passing or bouncing? Passing. Okay, and I also have x equals -2, right? X equals -2 has multiplicity what? Well, the multiplicity of x equals -2, -2 is the zero corresponding to this factor, and it has multiplicity 2, right? So I have multiplicity 2, which means I'm going to have what? Passing or bouncing? I'm going to have bouncing. Why bouncing? Because 2 is an even number. Okay, next up, x equals 2 has multiplicity 1. And that means we're going to have passing behavior, yeah? Okay, so that's 2 checked off. Last thing to do is to find the y-intercept. How do I get the y-intercept? I just plug in 0, f of 0. What do I get when I plug in 0? Well, I get -4 times 2 times -2. Is it clear how I got that? I put in a 0 for x. Here, here, and here. So I got 4 and 2 and -2, and I can't forget that negative sign, right? So what is the y-intercept? F of 0 is equal to positive 16, right? Because this negative sign and this negative sign cancel, and then we get 4 times 2 is 8 times 2 is 16. Sorry. Oh, yeah, thanks. I missed a square, didn't I? So it should not be 16. It should be 32. Thanks. Okay, so I know that the y-intercept is 32. Okay, so let's put the zeros on here, and then we'll finish up graphing this. So I know x equals -4. Maybe I'll put that there. And then I'll put x equals -2 right there. And then I'll put x equals 2 right there. So what do I know? I know that before I come up to this point, okay, after I pass through this, I have to be going down because of the end behavior, right? And there's no other zeros over here, right? I can't go up because I know eventually I'm going down. If I were to go up and then eventually down, I would have another 0. But I don't have another 0, so I know I must be going down from here. So what I'm going to do is just move this over a little bit so that it looks like I'm going to come through. Yeah, I'm going to come through this point. Okay, now I need to figure out what happens at the next 0. In order for the function to be 0 at this point, I definitely have to turn around, right? I have to turn around. Okay, and then I need to decide what's going to happen at the 0. Am I going to turn around and go through? No, because this 0 has multiplicity 2. Which means I should have bouncing. So I should not turn around and go through. I should turn around and bounce off. Like so. Okay? And that makes a whole heck of a lot of sense. Why does that make sense? Because the y-intercept, that's the next point. The y-intercept is at 0, 32. If I had gone through, there's no way I could make it back up to 0, 32, could I? So I come back and I go to 0, 32. And then what happens? I need to go through this 0, which means I need to turn around again, yeah? I need to turn around again and go, should I go through this one or should I bounce off? We should go through because x equals 2 has multiplicity 1, which means we should have passing behavior. So I'm going to fill this off like that, and I'm happy with the end behavior because as I go really far to the left, as I go really far to the left, the function goes really far down. As I go really far to the right, the function goes really far down, which is exactly what I determined with these limits, right? And I have all of my zeros. The function is 0 at all the zeros. The function touches the y-intercept, and it has the appropriate passing or bouncing behavior at each of the zeros. So this is about as good as we can get of a graph of this polynomial. Let's see how we did. So what is it? Someone Does someone have this written down who can dictate it to me? Actually, I think I remember what it was. It was, I can do this. It was negative, and then x plus 4. Geez, I'm so slow at this. X plus 4, and then we had x plus 2 squared, right?
Yeah.
And then we had x minus 2. Yeah? And that was it. Okay, let's see how we did. All right, not bad. We missed a little bit here in terms of we should have gone a bit higher, right? Because we turned around at 32. But there's no way to know whether that's the maximum or whether it keeps going up or whether we were already on the way down. We got the best important features of this graph, right? Which is we go through at -4, right? That's over here. We go through at -4, we come up, and then we turn around, we bounce at -2, we go up, and then at some point we turn around. I got 2 minutes left. Calm down. At some point we turn around. Where have I gone? Jesus. At some point we turn around, and then we go back down through x equals 2, right? So I just want to reiterate one more time. The steps here, we need to take into account end behavior, what are the zeros, and whether we have multiplicity even or odd. We need to find the y-intercept, and then as long as our graph contains each of these, it's going to be pretty good, right? It's not perfect, but it's pretty good. Okay, so that'll be it for today. Thanks for your attention.